So here's our final video for our Spring 2025 MAE 318 lab. Members of the lab and our objectives. So we are all junior mechanical engineering students at ASU, and it consists of Mason Macias, Caitlin Ely, and Jonathan O. And the objectives of this lab are to design a controller to meet specifications and choose between different types of controllers for the best results. So here are the customer specifications for this lab. The device must reach speed of 12 radians per second. The under or overshoot should be less than 2%. There needs to be comfortable acceleration, meaning the rise time is larger than 0.1 seconds. The controller must limit the jerk, meaning the initial slope of the graph is small. It must reach desired speed fast, meaning 2% settling time that is less than 0.2 seconds, and the controller must be energy efficient, meaning the voltage required is less than 24 volts.
All right, so this is our process for how we design our controller. In lab one, we primarily focused on determining the coefficients for a mathematical model, specifically B naught, B, and K sub t. And for lab two, we continued with this parameter determination with the R sub A and K sub E. And then we found the relationship between the AC value and the actual voltage or V sub A sent to the DC motor. And then we found the step response behavior by applying a constant voltage to the motor. And then finally, we found tau and K sub DC theoretically following the determination of the previous parameters. And below you can see in figure one is our mathematical model. Okay, for lab three, we found our frequency response by applying a sinusoidal voltage rather than a constant voltage. And this response was modeled using two Bode plots. The first one was found using theoretical methods, which was using our tau and K sub DC determined previously. And then the second plot was found experimentally using the output velocity data from the motor. And then using these plots, we were able to find our transfer function. We also found our proportional controller gain constant K sub p for the desired disk speed. And then over the course of this lab, we determined that the proportional controller was not ideal for the system due to the high voltage requirement to minimize error and its inability to compensate for disturbances. In the next lab four, using the transfer function, we were able to test the PD controller, PI controller, and a PI controller with the low pass filter. Finally, in lab five, we tested our PID controller, and we determined that the regular PI controller was the ideal controller.
So for controller choice, we chose a proportional integral controller, just a PI. This minimized the steady state error and had a fast settling time. It had a good balance of simplicity and it also gave us a good performance. We assumed that it had constant parameters and was modeled as a first or second order system. For this, we just used first order. The trade-offs, however, we experienced a slower settling time with increased overshoot. For here, using the CISO tool in lab five, we were able to complete two different controllers. The one on the left was a PI controller with the gains and the pre-filter time constant. And this is the one that we ended up using because it gave us better data. But the one on the right is using our data from the previous labs, which was a PID controller, but it was a lot more difficult to create and it had a lot more error. So a controller recommendation for us, proportional is fast response and minimal design, which is much easier to use. However, it has a lot of overshoot and it won't be able to eliminate the steady state error. PI controllers can completely eliminate the steady state error, and it's also very effective at rejecting disturbance. However, it has a slower settling time with increased overshoot as well. PD controllers will reach steady state faster and has better damping, but however, it will not completely eliminate the steady state error and won't be susceptible to disturbance. And finally, the PID controller is uh, easier to tune, but it's a lot more difficult to create than the other three. And linear performance is bad and requires much trial and error.
In terms of innovation, PI controllers can be used in many real world applications because they're accurate and a stable control, and they can easily respond to different changing conditions. So, a couple examples that we found to use PI controllers in the real world can be to use in heating and cooling applications like smart home devices, as shown on the right. Automated agriculture devices that can be used in simpler systems, as shown below, is a water pump, cruise control or automated driving systems like the motor, and finally, aircraft flight control systems. And that is it.